What came before the Big Bang? That's the question, isn't it? And it sounds simple enough. What was there before everything began? But here's the thing. The question itself might not make sense. And I know that sounds like a cop-out, like we're dodging the issue. But hear me out. Time itself started with the Big Bang. At least that's what our best physics tells us. Time and space, they came into existence together. They're woven into the same fabric. So asking what came before time is like asking what's north of the North Pole. Once you're at the northernmost point on Earth, the concept of north stops making sense. Every direction from there is south. According to general relativity, Einstein's masterpiece, the Big Bang wasn't an explosion that happened somewhere in space. It was the beginning of space itself, the origin of the cosmic stage on which everything plays out. So when we try to peer beyond that moment, beyond t equals 0, we're trying to look beyond the edge of existence as we understand it. The equations take us back closer and closer to that initial instant. And what they show us is fascinating and terrifying at the same time. Everything compressed. All the matter, all the energy, all the space in the universe squeezed into an infinitesimally small point. A singularity, we call it. Infinite density, infinite temperature. But here's where the trouble starts. Infinity is a red flag in physics. When your equations spit out infinity as an answer, it's usually telling you that your theory has reached its limit, that you're asking it to describe something it wasn't built to handle. And that's exactly what happens with general relativity at the Big Bang. The theory breaks down, it stops working, the math becomes meaningless, so we can't actually see what happened at t equals 0, not with our current understanding. There's a wall there, a boundary we can't cross with the tools we have. Maybe time really did start at that moment, and there simply wasn't a before. Or maybe there was something, but it's so fundamentally different from what we understand as time that our language and concepts can't grasp it. Think about it this way. Our brains evolved to deal with everyday things, finding food, avoiding predators, understanding cause and effect in our immediate environment. We're really good at that. But when it comes to the origin of time itself, we're way out of our depth. It's like trying to imagine a color you've never seen. Your brain just doesn't have the equipment. Still, we keep pushing, we keep asking, because that's what we do. Even if the answer is that there are some things we might never fully understand, we want to know where the boundaries are. We want to map the edges of knowledge. And maybe, just maybe, those edges are movable. Maybe with new physics, with a better understanding of how gravity and quantum mechanics work together, we'll be able to peer past that barrier to see what, if anything, existed before our universe began its expansion. But for now, we're left with this beautiful, frustrating mystery. The place where everything started, the moment when time itself was born. And beyond it, maybe nothing. Maybe something we can't even conceive of. Maybe silence. So if we try to push beyond that boundary, if we try to imagine what could have existed before the Big Bang, we need to think differently. Radically differently. And some scientists have done exactly that. They proposed ideas that sound wild, almost science fiction, but they come from serious physics, from real equations. One idea is that the universe cycles, that what we call the Big Bang wasn't actually the beginning, but a bounce, a transition from a previous state. Imagine the universe expanding like it is now, but then eventually the expansion slows, stops, reverses. Everything contracts back down. But instead of collapsing into a singularity and ending, it reaches some minimum size and then bounces back out again. A new Big Bang, a new cycle of expansion. In this model, time doesn't have a beginning. It extends infinitely into the past and future, with universe after universe, cycle after cycle, each one potentially lasting hundreds of billions of years. Our Big Bang would just be the most recent bounce in an eternal cosmic rhythm. The math for this is tricky. And there are problems with it, things that don't quite work yet. But it's being explored seriously because it offers a way around that singularity problem. If the universe never actually reaches infinite density, if it bounces before it gets there, then maybe the equations don't break down. Maybe we can actually describe what happened. Then there's the multiverse. And I know, this one sounds especially wild, but it comes from taking certain theories seriously, particularly the idea of eternal inflation. The basic notion is that our universe, everything we can see and measure, is just one bubble in a vast foam of universes. Each bubble, with its own Big Bang, its own laws of physics potentially, its own history. In this picture, Big Bangs are happening all the time, constantly, throughout this higher dimensional space. New universes budding off, inflating, creating their own space and time. We just happen to live in one particular bubble. And the reason we can exist here, the reason the laws are right for stars and planets and life, might just be selection bias. We're here because this is the kind of universe where observers can exist. It's not that this universe was made for us. It's that of all the universes that exist, we naturally find ourselves in one where we can exist. It's like asking why you were born in a hospital instead of, say, the middle of the ocean. Well, because hospitals are where humans give birth. The answer is almost tautological. Some people don't like this answer. It feels unsatisfying. We want to know why the universe has the specific properties it does, not just that it could have been different. But if the multiverse is real, if there really are countless universes with different properties, then maybe that's the only answer we're going to get for some question. There's also this idea from quantum mechanics that universes can arise spontaneously from nothing. And when I say nothing, I mean something very specific. I mean a quantum vacuum, which isn't actually empty. It's seething with energy, with virtual particles popping in and out of existence on timescales so short we can barely measure them. The laws of quantum mechanics allow for fluctuations, temporary violations of energy conservation, as long as they're brief enough. And some physicists have proposed that our entire universe could be one of those fluctuations, one that happened to grow instead of disappearing. A quantum fluctuation that inflated into everything we see. It sounds absurd, but the math works, at least in principle. The total energy of the universe might actually be zero. Matter and radiation have positive energy, but gravity has negative energy. They might balance out exactly, which means you're not creating something from nothing, you're just separating the positive and negative parts of zero. Whether any of this is right, we don't know. These are speculative ideas, tentative models built on extrapolations of physics we do understand. But they show that the question, what came before, isn't necessarily unanswerable. It just requires new ways of thinking, new frameworks that go beyond everyday intuition. And that brings us to a deeper problem. The reason we need these exotic ideas in the first place. General relativity works beautifully for planets, stars, galaxies. It describes gravity as the curvature of space-time, and it does it with incredible precision. But it's a classical theory. It doesn't incorporate quantum mechanics, the physics of the very small. And at the Big Bang, both matter. You've got all the mass of the universe squeezed into a tiny space. That's where gravity dominates. That's relativity territory. But it's also incredibly small and dense. That's where quantum effects become crucial. And we don't have a theory that combines the two. We don't have quantum gravity. That's the missing piece, the holy grail of theoretical physics. A framework that describes how space-time behaves when quantum effects can't be ignored. And without it, we can't really describe the first moments of the Big Bang. We can get close. We can model the universe from a tiny fraction of a second after the Big Bang began. But that first instant, that's still out of reach. People are working on it, lots of smart people. String theory is one approach, suggesting that particles are actually tiny vibrating strings, and that space-time has extra dimensions we can't see. Loop quantum gravity is another, proposing that space itself is quantized, made of discrete units like a fabric woven from loops. Both approaches suggest that the Big Bang singularity might not be a singularity at all, that there's some minimum size, some quantum limit that prevents infinite density, and if that's true, then maybe we can describe what happened. Maybe we can peer all the way back to the beginning, or the bounce, or whatever it was. But we're not there yet. We're still working on the theory, still trying to find ways to test it. Because that's the thing about physics. It's not just math. It's not just elegant equations. It has to match reality. It has to make predictions we can check. And until we can do that, these ideas remain possibilities. Intriguing, maybe even beautiful, but not confirmed. So where does that leave us? With a question that's partly answered and partly not. We know the universe had a beginning in the sense that time and space started expanding 13.8 billion years ago. We can trace that expansion back incredibly far to when the universe was a fraction of a second old. But the very first instant, the moment of origin itself, that's still mysterious, still beyond our grasp. And maybe it always will be. Or maybe the next generation of physicists will crack it. We'll find the right theory, make the right observations, and finally understand what, if anything, came before. Now, here's where things get interesting. Where does God fit into all of this? Into a universe that might be eternal, or that might have sprung from quantum fluctuations, or that might be one bubble in an infinite multiverse? It's a question people ask me all the time. And I think the honest answer is that science can't answer that question. Not directly. Science is a method. It's a way of understanding the natural world through observation and experiment. You make measurements, you build models, you test predictions, and within that framework, we've learned an enormous amount. We've measured the age of the universe. We've mapped the cosmic microwave background. We've traced the evolution of stars and galaxies. We've discovered the laws that govern matter and energy. But science doesn't tell you why those laws exist. It doesn't explain why there's something rather than nothing. It describes how things work, not why they're there to work in the first place. That's a deeper question, a philosophical question maybe. And it's beyond the scope of what science was designed to do. So when people ask me about God, I tell them this: the universe is 13.8 billion years old. We know that. We've measured it multiple ways, and the answers agree. The Earth is about 4.5 billion years old. We've dated rocks, we've studied radioactive decay, we've examined meteorites. The evidence is overwhelming. If your belief system requires the universe to be 6,000 years old, then you've got a conflict, not between science and religion necessarily, but between science and a particular interpretation of religious texts. And at that point, you have to decide which evidence you're going to accept. But if your belief system is compatible with what we've observed, if it accepts the age of the universe and the laws of physics and the evidence for evolution, then there's no inherent conflict. You can believe that God set the whole thing in motion, that the Big Bang was an act of creation, that the laws of physics are divine ordinances. Science doesn't rule that out. What science does is push the boundary of I don't know further back. We used to not know how stars shine. Now we do. Nuclear fusion. We used to not know how the moon formed. Now we have a pretty good idea. Giant impact. Every time we answer a question, the frontier moves. But there's always another question beyond it. Why do the laws of physics have the form they do? Why is the speed of light exactly what it is? Why does the electron have the mass it has? We don't know. Maybe someday we will. Maybe there's a deeper theory that explains all of it. Or maybe those are just the fundamental parameters of our universe. And the only answer is that's how it is. And if you want to call that God, if you want to see the hand of the divine in the structure of reality, I'm not going to tell you you're wrong. I can't. That's a question beyond science. What I will tell you is that science has given us this incredible gift, the ability to look back nearly 14 billion years, to see the universe when it was just 380,000 years old, when it first became transparent to light, to understand how atoms formed, how stars ignited, how galaxies assembled. We can trace our origins back through time, back through the formation of the solar system, through the deaths of earlier generations of stars that forged the heavy elements, back through the first stars that lit up the cosmos, back through the cosmic dark ages, all the way to the Big Bang itself. That's astonishing. That's a story written in light and atoms and mathematics. And whether you see that story as purely natural or as the unfolding of a divine plan, the story itself is awe-inspiring. The universe is vast. It's ancient. It operates according to laws we can discover and understand. And we're part of it. We're made of atoms forged in stars. We're the universe looking at itself, trying to understand itself. Maybe the question isn't whether there's room for God in the universe. Maybe the question is whether there's room for wonder, for humility, for the recognition that despite all we've learned, there's still so much we don't know. And maybe that's where meaning lives. Not in having all the answers, but in the search itself. So I guess what I'm saying is this: science and spirituality don't have to be enemies. They can coexist, they can even complement each other, as long as both are honest about their domains. Science tells us how the universe works. Religion, philosophy, they address why it matters, what it means to be conscious beings in a vast cosmos. And honestly, we need both. We need the rigor of science to understand reality. And we need the wonder, the meaning-making that comes from religion and philosophy and art to make sense of our place in that reality. The problem only arises when we confuse the two. When we try to use ancient texts as science textbooks, or when we claim science has all the answers to questions it was never designed to address. The universe is big enough for both, mystery enough for both, And the conversation between them, when it's done honestly and respectfully, can be incredibly rich. There's something else worth considering here. The sheer improbability of our existence. Not in a religious sense necessarily, but in a statistical one. Think about all the things that had to go right for us to be here having this conversation. The universe had to have the right laws of physics. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. Slightly weaker, and stars might not form at all. If the strong nuclear force were different by just a few percent, atoms wouldn't be stable. Carbon, oxygen, all the elements we're made of, they wouldn't exist. Then you need a star like our Sunday, not too big, not too small. Big stars burn hot and die young. Small stars are dim and unstable. You need something in the middle, something that can shine steadily for billions of years. You need a planet in the right orbit, close enough to the star to be warm, but not so close that water boils away, far enough that it doesn't freeze solid. And you need that planet to be the right size. Too small and it can't hold an atmosphere. Too large and it becomes a gas giant. You need a moon to stabilize the planet's tilt, giving you stable seasons. You need plate tectonics to recycle nutrients and regulate climate. You need a magnetic field to protect against radiation. You need Jupiter out there with its massive gravity sweeping up asteroids and comets that might otherwise bombard the inner solar system. And even with all that, you need chemistry to organize itself into something that can replicate. You need evolution to have billions of years to work. You need mass extinctions to clear out ecological niches so new forms can emerge. You need one particular lineage of apes to develop bigger brains, to start using tools, to develop language and culture and science. The odds of all of that happening by pure chance seem astronomically small. So small that some people see it as evidence of design, of purpose, and I understand that instinct. It does seem miraculous, but here's another way to think about it. In a universe this vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars, improbable things happen all the time. Somewhere, the question isn't whether life is likely on any given planet. It's whether the universe is big enough and old enough for it to happen at least once. And clearly it is, because we're here. We're the evidence that it's possible. Whether that means the universe was designed for life, or whether it just means the universe is big enough that even incredibly unlikely things occur eventually, that's a question science can't definitively answer. Both interpretations are compatible with the observations. What we can say is this: we're lucky. Cosmically, unbelievably lucky. Whether that luck comes from divine providence or from living in a universe so vast that even miracles become inevitable, the result is the same. We exist. Against all odds, we're here. And that should fill us with gratitude and wonder. Not complacency, but appreciation. For the delicate balance of forces that allows atoms to form, for the stars that cook up heavy elements, for the planets that provide stable homes, for the chemistry that enables life, for the evolution that crafted consciousness. We didn't earn this. We couldn't have. We're the beneficiaries of 13.8 billion years of cosmic history. And the least we can do is try to understand it, to appreciate it, to not squander it. Now let's talk about something that keeps me up at night. Something that should keep everyone up at night. The Fermi paradox, named after Enrico Fermi, the physicist who asked a deceptively simple question over lunch one day, 1950. Where is everybody? Here's the thing. There are hundreds of billions of stars in our galaxy alone. Hundreds of billions. And we now know that planets are common. Most stars have them. We found thousands of exoplanets, and we've barely scratched the surface. Some of those planets are in the habitable zone, the right distance from their star for liquid water to exist on the surface. So if planets are common, and some are habitable, then shouldn't life be common too? And if life is common, then some fraction of it should evolve intelligence. And some fraction of intelligent life should develop technology. Radio telescope, spacecraft, interstellar communication. The math seems to say that there should be thousands, maybe millions of technological civilizations in our galaxy alone. Even with very conservative estimates, even if you assume that only a tiny fraction of planets with life develop intelligence, and only a tiny fraction of intelligent species survive long enough to spread across the stars. And yet, when we look up at the sky, when we listen with our radio telescopes, we hear nothing. Silence. No signals. No evidence of vast engineering projects. No signs that anyone else is out there, and that's the paradox. The math says they should be there. The sky says they're not. So what's going on? Why is it so quiet? There are a lot of possible answers, and some of them are pretty disturbing. Maybe life is rare. Maybe the jump from chemistry to biology is incredibly unlikely. We don't actually know how life started on Earth. We have ideas, hypotheses, experiments that show how some of the building blocks could form naturally. But the complete process, from non-living molecules to the first self-replicating cell, that's still a mystery. Maybe it's so unlikely that it's only happened once in the observable universe. That would make us incredibly special and incredibly alone. Or maybe life is common, but intelligence is rare. Maybe most life stays simple. Bacteria and algae, creatures without brains or technology. Even on Earth, it took billions of years for complex multicellular life to evolve. And intelligence, tool use, technological civilization, that only happened once in one species in the last few million years out of 4 billion years of life. Maybe we're the exception, not the rule. Think about it. Life appeared on Earth almost as soon as conditions allowed, about 3.8 billion years ago. But complex life, multicellular organisms, only showed up about 600 million years ago. That's a gap of over 3 billion years. And even after complex life emerged, it took another 600 million years to produce a species capable of asking these questions. So maybe the filter, the barrier that's hard to cross, isn't the origin of life. Maybe it's the jump to complexity, or the jump to intelligence, or the jump from intelligence to technology. Each one might be incredibly unlikely. Or maybe civilizations destroy themselves. Maybe there's something about the nature of intelligence and technology that's self-limiting. Nuclear weapons, climate change, artificial intelligence, bioweapons, nanotechnology run amok. Maybe every civilization reaches a point where they have the power to destroy themselves, and most don't make it through. Maybe we're approaching that point right now. That's a sobering thought. That every time a species develops radio telescopes, they also develop the means of their own extinction. And the window where they're both technological enough to communicate and still alive to do it might be very narrow. Maybe a few hundred years. A blink of an eye on cosmic timescale. Look at us. We've had radio for barely over a century. We've had nuclear weapons for less than a century. We're already facing existential risks from climate change, from artificial intelligence, from engineered pathogens. Can we survive another century? Another millennium? It's not guaranteed. And if we can't, if we're typical, then maybe the galaxy is littered with the ruins of civilizations that rose and fell, that briefly reached out into the cosmos and then went silent. Archaeological sites on distant worlds, waiting for someone to find them. But no one's still broadcasting. No one's still alive. Then there's the zoo hypothesis. Maybe they're out there, but they're deliberately not contacting us. Maybe there's some kind of galactic ethics, a prime directive like in Star Trek, where advanced civilizations don't interfere with younger ones. They watch, maybe, but they don't make contact until we reach some threshold of maturity. That would explain the silence, but it requires assuming a lot about alien psychology and ethics. Why would all civilizations follow the same rule? And what would that threshold be? Or the dark forest hypothesis, which is even more chilling. Maybe the galaxy is full of civilizations, but they're all hiding, staying quiet, because the universe is dangerous, and broadcasting your location is a risk. Maybe any civilization that announces itself gets wiped out by older, more powerful civilizations who see newcomers as threats or competition. So everyone stays silent, listening but never speaking, like hunters in a dark forest, trying not to reveal their position. I don't love that explanation. It's pessimistic. It suggests the universe is fundamentally hostile, that contact between civilizations is more likely to end in violence than cooperation. But I can't rule it out. We don't know enough about how alien minds would work, what their motivations might be, or maybe they're just not interested in us. Maybe we're like ants to them, not dangerous, not particularly interesting, just there. Do you try to communicate with ant colonies? Probably not. Not because you hate ants, but because there's no common ground, nothing to say. You're operating on completely different levels of complexity. Maybe that's how advanced aliens see us. We're barely out of the trees, cosmically speaking. We've had technology for a few thousand years at most. Radio for barely over a century. Space travel for less than that. Maybe to a civilization that's 1 million years old, we're not even worth the effort of saying hello. Or maybe, and this is the really wild one, maybe in the entire galaxy, we're the first civilization to reach this level of technology. It had to happen to someone first. after all. The universe is 13.8 billion years old, but stars like our sun only started forming in large numbers a few billion years ago. The first generations of stars didn't have planets with heavy elements. No carbon, no oxygen, no iron. You need several generations of stars to build up those elements through nuclear fusion and supernova explosions. So maybe the conditions for technological life have only recently become common, and we're early, pioneers, the first to look up and ask these questions. If that's true, then the galaxy is ours to explore, to settle, to fill with life and intelligence, but it also means we're alone, at least for now, at least in this part of the universe. The responsibility that comes with that is enormous. If we're the only ones who made it this far, then the future of intelligence in the galaxy might depend on us, on whether we survive our own adolescence as a species, on whether we make it past the filters that might have stopped others. We don't know which of these answers is right. Maybe none of them. Maybe it's something we haven't thought of yet. Something that will only make sense once we know more about biology and evolution and intelligence. But the search continues. SETI, the search for extraterrestrial intelligence, has been listening for decades now, scanning the skies, looking for signals that couldn't be natural, patterns that would indicate intelligence, narrowband radio emissions, repeating pulses, anything that stands out from the cosmic background noise. And the technology keeps getting better. We're not just listening to radio anymore. We're looking for laser pulses, brief flashes of light that might be attempts at optical communication. We're looking for megastructures around stars, vast constructions that would block starlight in unusual patterns, Dyson spheres or swarms, solar collectors that harvest most of a star's energy. We're studying exoplanet atmospheres, looking for chemical signatures that might indicate industrial civilization, pollutants that don't occur naturally, chlorofluorocarbons, nitrogen dioxide, things that only technology produces in large quantity, or even biosignatures, combinations of gases like oxygen and methane that together suggest biological activity. We're casting a wider net, being more creative about what we're looking for, because maybe they're not using radio. Maybe that's a technological dead end, something civilizations use briefly before moving on to something better. Maybe they're using neutrinos or gravitational waves or some form of communication we haven't even imagined yet. And we're looking closer to home too, at the moons of Jupiter and Saturn. Europa and Enceladus have liquid water oceans beneath their icy shells. That water has been liquid for billions of years, isolated from the surface, possibly harboring life that evolved independently from Earth. If we found life there, even simple microbial life, it would suggest that life arises readily whenever conditions allow, that the universe might be teeming with, or we might find nothing. We might keep looking for centuries and never detect a signal, never find evidence of anyone else. And that would be profound too. It would suggest we're rare, maybe alone. The only eyes in the galaxy looking up and wondering. Either answer changes everything. If we find them, it means we're part of a cosmic community. We're not unique. Intelligence and technology arise naturally, inevitably, given enough time. And that raises new questions. What are they like? How do they organize their societies? What have they learned that we haven't? Could we communicate, trade ideas, visit each other? But if we don't find them, if the silence continues, then we're it. The universe's experiment in consciousness has succeeded exactly once, as far as we know. And that means we matter enormously. Because if we fail, if we destroy ourselves or fade away, it might be billions of years before another species gets this far. The universe would be darker for our absence. So we keep listening, keep watching, keep searching, because the answer, whatever it is, tells us something fundamental about our place in the cosmos. And that's worth knowing. Let me tell you about quantum mechanics, because this is where physics gets truly strange, where our everyday intuitions completely fail us, where the universe reveals itself to be far weirder than we ever imagined. At the start of the 20th century, physics seemed pretty well figured out. Newton's laws described motion with incredible precision. You could predict the orbits of planets decades in advance. Maxwell's equations unified electricity and magnetism, explained light as electromagnetic waves. Thermodynamics told you how heat and energy flowed. Everything fit together beautifully. But then people started looking at things more carefully, at the very small, at how atoms behaved, how light interacted with matter, and things stopped making sense. There was this problem with blackbody radiation, with how hot objects glow. Classical physics said they should emit infinite energy at short wavelengths. which obviously didn't happen. That was the ultraviolet catastrophe. Max Planck solved it in 1900 by proposing something radical. That energy comes in discrete chunks in quanta, not a continuous flow, but packets. It was just a mathematical trick at first, a way to make the equations work. But then Einstein took it seriously. He used it to explain the photoelectric effect, how light knocks electrons out of metal. And the only way to explain the observations was if light itself came in particles, in photons. Each photon carrying a specific amount of energy determined by its frequency. So light, which we thought was a wave, also behaved like a particle. That was weird enough. But then de Broglie proposed that particles, things like electrons, could also behave like waves. And experiments confirmed it. You could send electrons through two slits, and they'd create an interference pattern, just like waves do. So particles are also waves. Waves are also particles. Nothing is what it seems. Welcome to quantum mechanics. Heisenberg made it even stranger with his uncertainty principle. You can't know both the position and the momentum of a particle with perfect precision. The more accurately you measure one, the less accurately you can know the other. And this isn't a technological limitation. It's not that our instruments aren't good enough. It's fundamental. The particle doesn't have both properties simultaneously. They're undefined until you measure them. Think about what that means. At the most basic level, reality is fuzzy, uncertain. You can't predict exactly what will happen, only the probability of different outcomes. Einstein hated this. God does not play dice with the universe, he famously said. But the universe doesn't care what Einstein thought. It plays dice. Then there's superposition. A particle isn't here or there. It's both. Until you measure it. Then it's one or the other. Schrödinger illustrated this with his famous cat thought experiment. You put a cat in a box with a quantum trigger connected to poison. According to quantum mechanics, until you open the box and look, the cat is both alive and dead. Both states exist simultaneously. Nobody actually believes cats exist in superposition. But where's the boundary? At what point does quantum weirdness give way to classical certainty? We don't know. It's called the measurement problem and has been debated for almost a century. And then there's entanglement. Einstein called it spooky action at a distance and thought it proved quantum mechanics was incomplete. Here's how it works. You create two particles in an entangled state. They're connected, correlated in a deep way. Then you separate them, light years apart if you want. When you measure one, the other instantly responds, changing its state to maintain the correlation. Instantly. Faster than light could travel between them. It seems to violate relativity, which says nothing can go faster than light. Except it doesn't quite, because you can't use entanglement to send messages. You can't control what result you get when you measure, so you can't encode information. But the correlation is real. We've tested it over and over. It's one of the most precisely verified predictions in all of physics. So what does it mean? That the universe is non-local, that distant objects can be connected in ways that don't respect our usual notions of space and separation. That reality at its deepest level is fundamentally interconnected in ways we're still trying to understand. Now, you might think, okay, this is all very strange, but it only matters for tiny things. Atoms and electrons. It doesn't affect me. But you'd be wrong. Quantum mechanics is everywhere in your daily life. Your phone's processor relies on quantum tunneling, where electrons pass through barriers they classically couldn't. Every transistor depends on it. Lasers work through stimulated emission, a quantum process, LEDs, solar panels, MRI machines, all quantum technology. We've built our entire modern civilization on top of quantum mechanics. And we're going further. Quantum computers use superposition and entanglement to perform calculations impossible for classical computers. A quantum bit, a qubit, can be both 0 and 1 simultaneously. And when you have many qubits entangled together, the number of states they can represent grows exponentially. 100 qubits can represent more states than there are atoms in the universe. We're building these machines right now. Google, IBM, startups, research labs, they're small, fragile, error-prone. But they work. They can solve certain problems much faster than any classical computer. Simulating quantum systems, breaking encryption, optimizing complex systems. The potential is enormous. There's also quantum cryptography. Because of the no-cloning theorem, you can't copy a quantum state without destroying it. That means you can detect eavesdropping. If someone tries to intercept a quantum communication, they leave traces. It's physically impossible to spy on without being caught. Banks and governments are already deploying quantum-secure communication networks. But even with all these applications, the deeper questions remain. What is quantum mechanics really telling us about reality? There are different interpretations, different ways of making sense of the math. The Copenhagen interpretation says particles exist in superposition until measured, then the wave function collapses. But what counts as measurement? Does it require consciousness? Probably not, but we're not sure. The many worlds interpretation says the wave function never collapses. Every possible outcome happens, but in different branches of reality. When you measure a particle's spin, the universe splits. In one branch, you see spin up. In another, you see spin down. Both are real, both exist, we just can't access the other branches. Pilot wave theory says particles always have definite positions, but they're guided by a wave that fills space. It's deterministic, no randomness, but it requires faster than light influences. We don't know which is right. They all make the same predictions, so we can't distinguish experimentally. It comes down to philosophy. Which kind of strangeness are you willing to accept? The measurement problem remains unsolved. Why does observation change things? What's special about measurement? Some say it's decoherence, the interaction with the environment that effectively measures quantum systems. But that just pushes the question back. When does decoherence count as measurement? These aren't just abstract puzzles. As we build bigger quantum systems, as we try to maintain superposition in larger objects, we're probing the boundary between quantum and classical. We're testing where quantum mechanics stops applying. And it's not clear there's a sharp line. Maybe the lesson is this. The universe at its most fundamental level doesn't look like anything we experience. It's not made of solid, definite things. It's made of probabilities, of possibilities, of relationships. Observation doesn't just reveal reality, it participates in creating it. Particles can be connected across vast distances. The universe might be constantly splitting into parallel versions, and yet it works. The predictions are stunningly accurate. We can calculate the magnetic moment of the electron to 10 decimal places and get it right. We can predict the energy levels of atoms, the behavior of semiconductors, the properties of new materials. Quantum mechanics is the most successful scientific theory ever developed. So we use it. We build technology with it, even as we struggle to understand what it really means. And maybe that's okay. Maybe the universe doesn't owe us intuitive explanations. Maybe our brains evolved to hunt and gather on the African savanna, just aren't equipped to grasp reality at its deepest level. But we keep trying, because that's what humans do. We push the boundaries, we ask the questions that don't have easy answers, and slowly, step by step, we uncover more of the truth. Now let's talk about string theory, because if quantum mechanics is weird, string theory takes it to a whole new level. This is physics at the absolute edge, where mathematics leads and experiment struggles to follow. Here's the fundamental problem. We have two great theories. General relativity describes gravity, space-time, the large-scale structure of the universe. It's been tested to incredible precision. We've detected gravitational waves, exactly as Einstein predicted. We've photographed black holes. The theory works, and we have quantum mechanics, which describes particles, forces, the behavior of matter at the smallest scales. It's also been tested exhaustively. It makes predictions accurate to many decimal places. It works too, but they don't fit together. When you try to combine them, when you need both quantum mechanics and general relativity, like in black holes or at the Big Bang, the math breaks down. You get infinities, meaningless results. The theories are incompatible. This is a problem. Because nature doesn't care about our theoretical boundaries. There are situations where both quantum effects and strong gravity matter. We need a theory of quantum gravity, a framework that works in both regimes. String theory is one attempt, and the core idea is elegant. What if fundamental particles aren't point-like? What if they're tiny string? Vibrating filaments of energy, incredibly small, far smaller than atoms. Different vibrations would correspond to different particles. One vibration pattern gives you an electron, another gives you a quark, another a photon. The universe is like a cosmic symphony. And every particle is a different note played on these fundamental strings. This idea has remarkable consequences. For one thing, it naturally includes gravity. One of the vibration modes corresponds to a graviton, the hypothetical particle that carries gravitational force. So gravity isn't something you add to the theory. It emerges automatically. That's huge. But there's a price. For the mathematics to be consistent, you need extra dimensions. Not just the 3 spatial dimensions we experience, plus time. You need 10 dimensions total, or 11 in some version. Where are these extra dimensions? The idea is they're compactified, curled up so small we can't detect them. Imagine a garden hose. From far away, it looks one-dimensional, like a line. Up close, you see it has thickness, a second dimension curled into a circle. Similarly, every point in our 3-dimensional space might have 6 extra dimensions curled up into a tiny shape. The exact shape matters. It affects how strings vibrate, which determines what particles exist and how they interact. Different shapes give different physics, and there are an enormous number of possible shapes. This leads to the landscape problem. If there are 10 to the power of 500 different ways to compactify the extra dimensions, then there are that many possible universes, each with different laws. And we happen to live in one where the laws allow stars and atoms and life, not because it was designed that way, but because we can only exist in universes with the right properties. Some physicists love this. It connects to the multiverse, suggests all these possible universes actually exist. Others hate it. If the theory can accommodate any observations, does it really predict anything? And that's the controversy. String theory is mathematically beautiful, internally consistent. It unifies all the forces. But we can't test it. The strings are too small. We'd need a particle accelerator the size of the galaxy to probe them directly. So we look for indirect evidence, patterns in the cosmic microwave background, unusual properties of black holes, gravitational wave signatures, anything that might hint we're on the right track. But so far, nothing definitive. The theory remains a promising idea, not established fact. Some physicists have devoted their careers to it. Others think it's a beautiful dead end, that the real theory will be something different. I'm agnostic. String theory has led to profound insights. Connections between black holes and quantum information, new mathematical tools, a deeper understanding of gauge theories. Even if it's not the final answer, it's taught us things. But I want testable predictions. I want evidence. Until we have that, it's mathematics and hope, not physics. Still, the search continues. People are working on it, pushing forward, looking for ways to test it. And maybe they'll succeed, maybe string theory will turn out to be right, or maybe we'll discover it was pointing in the right direction but missing something crucial. Or maybe the real theory of quantum gravity will be completely different, something we haven't imagined yet. Either way, the quest matters, because we're trying to answer the deepest questions. What is space made of? What is time? Why does the universe exist? These aren't idle curiosities. They're fundamental to understanding reality itself. So where does all this leave us? We've covered enormous ground. The origin of the universe, the search for life, the strange rules of the quantum world, the quest for a unified theory. And what emerges is a picture of reality, far stranger and more wonderful than anyone imagined. The universe began 13.8 billion years ago in an incredibly hot, dense state. It's been expanding ever since, cooling, forming structures, creating complexity. The stars are nuclear furnaces, fusing light elements into heavier ones. When they die, they scatter those elements into space. We're made of that stardust. Carbon, oxygen, nitrogen, all the atoms in your body were forged in stellar cores. The universe is mostly made of things we can't see. Dark matter that holds galaxies together. Dark energy that's accelerating expansion. We don't know what they are. They're among the biggest mysteries in science. We found thousands of planets around other stars, some inhabitable zones, some that might have conditions for life, but we haven't found life itself, not yet. The search continues. Quantum mechanics tells us reality at small scales is fundamentally probabilistic. Particles exist in superposition. They can be entangled across vast distances. The act of measurement changes things in ways we still don't fully understand. And we're still looking for the theory that unifies it all. That explains how quantum mechanics and gravity fit together. String theory is one possibility. Loop quantum gravity, another. Maybe the answer is something we haven't thought of yet. What's remarkable is how much we've learned. A few centuries ago, we thought the Earth was the center of everything. Now, we know we're on a small planet orbiting an average star in a typical galaxy, one of hundreds of billions. We've traced our cosmic history back to the first fraction of a second. We understand how stars shine, how galaxies form, how planets coalesce from dust. We've visited other worlds, landed robots on Mars, flown spacecraft past the edge of the solar system. We've discovered the laws that govern matter and energy. We can predict the motion of planets, the behavior of atoms, the evolution of stars. We've built technologies that would seem like magic to our ancestors. And yet we're just beginning. The universe is 13.8 billion years old. Earth is 4.5 billion. Modern humans have existed for perhaps 300,000 years. We've had science for a few centuries. In cosmic terms, we're infants, but we're learning. Every generation pushes the boundaries further. Every decade brings new discoveries, and the questions keep getting deeper. The search for meaning continues too. Understanding how the universe works doesn't diminish wonder. It enhances it. When you look up at the night sky and realize those points of light are distant suns, some with their own planets, some already dead, though their light still reaches us, it's breathtaking. When you understand that you're made of atoms forged in stellar explosions, that you're literally star stuff contemplating the stars, it's profound. When you grasp that the same laws that govern the planets also govern the atoms in your brain, connecting you to the cosmos in the most fundamental way, it's beautiful. Science doesn't steal mystery. It reveals deeper mysteries. Every answer opens new questions. Why these laws and not others? Why is there something rather than nothing? What is consciousness? Are we alone? We don't know. Maybe we'll never know all of it. But the search, the quest to understand, that's what makes us human. That's what distinguishes us from other species. We're the universe trying to understand itself. And whether you see that as a purely natural process or something imbued with deeper meaning, whether you're religious or secular, scientist or artist, we're all part of the same story. The cosmic story. The story of matter and energy organizing itself into stars and planets and life and consciousness. That story is still being written. We're living chapters in it. And what we do matters. How we treat each other, how we care for our planet, whether we survive our technological adolescence, these will determine what comes next. If we make it, if we navigate the challenges ahead, the future is ours. We could spread beyond Earth, become a multi-planet species, eventually a multi-star species. We could explore the galaxy, search for other life, learn things we can't even imagine yet. Or we could fail. We could destroy ourselves through war or environmental collapse or runaway technology. We could become a footnote in cosmic history, a species that briefly achieved consciousness and then squandered it. The choice is ours. And the stakes couldn't be higher. Because if we're alone, if we're the only minds in the galaxy asking these questions, then we matter more than we can possibly comprehend. We're not just observers of the cosmic story. We're participants, characters with agency who can influence how it unfolds. So look up at the stars, feel the connection to the cosmos, understand that you're part of something vast and ancient and ongoing, and then ask yourself, what will you do with that knowledge? How will you contribute to the story? Because in the end, that's what matters. Not just understanding the universe, but being worthy of that understanding. Not just acquiring knowledge, but using it wisely. Not just contemplating the cosmos, but being good stewards of the small piece of it we call home. The universe is waiting, full of mysteries to solve, wonders to discover, questions to answer, and we're just getting started. The thing about being human is that we exist in this strange intersection. We're small, cosmically insignificant in terms of size and lifespan. A human being is about 1 meter tall. The observable universe is about 90 billion light years across. That's a ratio so extreme it's hard to grasp. We're like a single atom compared to the entire Earth, and then some. We live maybe 80 years if we're lucky. The universe has been around for 13.8 billion years. Stars will keep shining for trillions more. On that timescale, our entire civilization, from the first cities to whatever comes last, is a brief flicker. And yet, despite being so small and so brief, we've managed to understand so much. We've figured out what stars are made of. We've measured the age of the universe. We've discovered the laws of physics. We've traced our ancestry back through billions of years of evolution, back through the formation of the Earth, back through the deaths of earlier stars, all the way to the Big Bang. That's astonishing. A species that evolved to find food and avoid predators has developed mathematics, physics, astronomy. We built machines that can detect gravitational waves from colliding black holes billions of light years away. We've sent our cameras to the edge of the solar system and beyond. How do we do it? Not through physical strength. We're weak compared to many animals. not through speed or durability, but through our ability to think, to reason, to build on what previous generations learned. Through language and writing and mathematics, we created a collective intelligence that transcends any individual. Science is humanity's most successful collaborative project. Thousands of people across centuries, each adding a piece to the puzzle. Galileo observing Jupiter's moons, Newton deriving the laws of motion, Faraday and Maxwell unifying electricity and magnetism, Einstein reimagining space and time, Hubble discovering the universe is expanding. Each built on what came before. Each saw a little further because they stood on the shoulders of giants, as Newton put it. And now we can see incredibly far. We can look back to when the universe was just 380,000 years old. We can predict the motions of planets centuries in advance. We can understand the quantum behavior of individual atoms. This is our legacy as a species, not empires or monuments, though those exist, but knowledge, understanding, the accumulated wisdom of generations of people trying to make sense of the world. And that knowledge has practical benefits too. Medicine that lets us live longer, healthier lives. Technology that connects us across vast distances. Agriculture that can feed billions. Material science that gives us everything from smartphones to spacecraft. But beyond the practical applications, there's something deeper. A satisfaction that comes from understanding. From seeing how the pieces fit together, from realizing that the universe, despite its vastness and strangeness, is comprehensible, that we can figure it out. There's beauty in that. In a mathematical equation that captures some fundamental truth. In an elegant theory that explains diverse phenomena. In the realization that distant galaxies obey the same laws as falling apples on Earth. Einstein said the most incomprehensible thing about the universe is that it's comprehensible. Why should the universe be understandable to us? Why should mathematics, a tool we invented, describe reality so perfectly? These are deep questions without clear answers. Maybe it's just because we're part of the universe, made of the same stuff, following the same laws. So of course we can understand it. We're not separate from nature, we're an expression of it. The universe understanding itself through us. Or maybe there's something deeper, some fundamental connection between consciousness and physics that we don't yet grasp. That's speculation. But it's interesting speculation. What's not speculation is that we can understand. We have understood an enormous amount. And there's more to learn, always more. The frontier keeps expanding. Think about what's happened just in the last century. We discovered quantum mechanics, relativity, the expansion of the universe, the Big Bang, DNA, plate tectonics, exoplanets, gravitational waves, the Higgs boson, each one a revolution in understanding. And we're not done. We're building bigger telescopes to see further into space and time, more powerful particle accelerators to probe smaller scale, quantum computers to solve problems beyond classical reach, space missions to explore the solar system and beyond. What will we discover in the next century? The nature of dark matter and dark energy, life on other worlds, a theory of quantum gravity, technologies we can't even imagine yet? I don't know. Nobody does. That's what makes it exciting. We're at the beginning of the story, not the end. There's so much we don't understand, so many questions without answers. And that's okay. That's wonderful, actually, because it means there's work for future generations, mysteries for them to solve, frontiers for them to explore. The adventure continues, but we need to make sure there are future generations. That's not guaranteed. We face challenges that could end human civilization, climate change, nuclear weapons, pandemics, artificial intelligence that might exceed our control, asteroid impacts, supervolcano eruptions. Some of these are natural risks, things that have happened before and will happen again. Others are risks we created ourselves. That's new. For the first time in Earth's history, a single species has the power to significantly alter the planet's climate, to cause mass extinctions, potentially to end complex life entirely. That's a heavy responsibility. And we're not handling it particularly well. We're still acting like tribes competing for resources, even though we're all on the same small planet with nowhere else to go. We're still thinking short term, even though the decisions we make now will affect generations to come. We need to do better. We need to think bigger, longer, more collectively. We need to recognize that we're all in this together, that national borders and ethnic divisions are human constructs, but the laws of physics and the fate of the biosphere are real. And we need to use the knowledge we've gained wisely. Science gives us power, the power to split atoms, to modify genes, to change the climate. But power without wisdom is dangerous. We need ethical frameworks that match our technological capabilities. This isn't just about avoiding catastrophe. It's about building a future worth having, a civilization that can thrive sustainably, that can explore the cosmos, that can solve the great mysteries, that can create art and beauty and meaning. We have the potential for that. We're clever enough. We have the tools. The question is whether we have the wisdom and the will. I'm optimistic, but not blindly so. History shows humans are capable of great things. We've overcome enormous challenges before. We've cooperated on massive scales when necessary. We've built institutions that span the globe. We've created knowledge that belongs to everyone. But history also shows we're capable of terrible things. War, genocide, environmental destruction, short-sighted greed. We contain multitudes, as Walt Whitman said, both angels and demons. Which will win out? I think that depends on us, on the choices we make individually and collectively, on whether we let our better nature guide us. And science can help, not by providing all the answers, because it can't. Questions of value, of meaning, of how we should live, those aren't scientific questions, but science can inform those decisions, can show us consequences, can expand our circle of concern to include future generations and other species. Science can also inspire, can fill us with wonder at the cosmos, can remind us how lucky we are to exist at all, can give us perspective on our place in the universe. When you understand that you're made of atoms forged in stellar explosions billions of years ago, that you're the product of an unbroken chain of life going back almost 4 billion years, that you're conscious matter capable of contemplating its own existence, it changes you. At least it should. It makes petty concerns seem smaller. National rivalries, ethnic hatred, greed and status seeking. What do these matter on a cosmic scale? We're all humans, all alive for a brief moment, all sharing this small world. Doesn't it make more sense to work together, to build something lasting, to try to ensure that the light of consciousness doesn't go out? I think it does. And I think most people deep down feel the same way. We're social creatures. We evolved to cooperate, to care for each other, to work toward common goals. The challenge is scaling that up, making it work for 8 billion people, for a global civilization with competing interests and limited resources, for a species that can now affect the entire planet. It's not easy, but nothing worthwhile ever is. And this is the most worthwhile thing imaginable: the survival and flourishing of intelligent life, the continuation of the cosmic story, because that's what we are. We're the universe's way of knowing itself, of experiencing beauty and wonder, of asking questions and seeking answers, of creating meaning in what might otherwise be just matter and energy following physical laws. Without consciousness, without minds to observe and appreciate, the universe would still exist. Stars would shine, galaxies would spin, atoms would vibrate according to the laws of quantum mechanics, but there'd be no one to know about it, no one to care. We make it matter by existing, by observing, by trying to understand. We're not just inhabitants of the universe, we're participants, part of how the universe experiences itself. That's profound, that's meaningful, not in some mystical sense necessarily, though you can interpret it that way if you choose, but in a real concrete sense, we matter because we make things matter. So when I look up at the night sky, when I contemplate the vastness of space and time, I don't feel insignificant. I feel connected, part of something vast and ancient and ongoing, and I feel responsible. Because if we're the only ones, or even if we're just one of a few, then what we do matters enormously. The choices we make ripple out across space and time. Will we be remembered as the species that reached for the stars, that solved the great mysteries, that brought life and consciousness to dead worlds? Or will we be a cautionary tale, a species that achieved knowledge but lacked wisdom, that had the power to do great things but squandered it? The answer isn't written yet. We're writing it every day through our choices and actions, through what we build and what we preserve, through how we treat each other and the world we inhabit. And that brings me back to where we started, to the questions that inspired this whole conversation. What came before the Big Bang? Where does God fit in? Are we alone? What is reality made of? These are profound questions, maybe the most profound questions we can ask. And we've made progress on all of them. Not complete answers, but progress. Understanding that deepens with each generation. We know the universe is 13.8 billion years old. We know it's expanding. We know the basic laws that govern matter and energy. We know we're made of stardust. We know that life evolved over billions of years from simple chemistry. We don't know what came before the Big Bang, if anything. We don't know if we're alone. We don't have a complete theory of quantum gravity. We don't know what consciousness really is, but we're working on it. Thousands of scientists around the world asking questions, running experiments, building theories, testing prediction, pushing the boundaries of knowledge a little further every year. And you can be part of that. You don't have to be a professional scientist. You can support science education. You can vote for policies that fund research. You can raise the next generation to be curious and thoughtful. You can appreciate the beauty of what we've learned. You can look up at the stars and wonder. You can ask questions. You can seek to understand. That's what it means to be human at our best. Curious, thoughtful, striving to comprehend our place in the cosmos. And maybe, just maybe, if we do that collectively, if we embrace our role as the universe's way of understanding itself, we'll not only survive, but thrive. We'll become something worthy of the cosmic gift of consciousness. We'll explore the galaxy, find other life, or spread life ourselves, solve the remaining mysteries, create wonders we can't yet imagine, build a civilization that lasts not just centuries, but millennia or millions of years. That's the dream. That's the potential. And it's within our reach if we choose to grasp it. So look up, wonder, ask questions, seek answers. And remember that you're part of something vast and beautiful and ongoing, the cosmic story. And your chapter, however brief, matters. The universe is waiting, full of mysteries and wonders. And we're the ones privileged enough to explore it, to try to understand it, to be amazed by it. That's not a bad way to spend a life. Not bad at all.